This morning, we have three distinguished speakers to talk about the theory and practice of artificial intelligence in imaging. And the first speaker, Dr. Geiger, could not come because of some medical problems in her family. So Dr. Kahn has graciously agreed to give her paper, topic on perspectives on AI and machine learning developments in cancer imaging.
Well, thanks very much. I'd like to give Mary Ellen's appreciation to the organizers and her sincere apologies that she wasn't able to be here, but as indicated, because of a family medical crisis, wasn't able to join us here. I just wanted to say personally, I've had the great pleasure of knowing Mary Ellen actually since I began in radiology. I did my radiology residency at University of Chicago. And when Mary Ellen was either a postdoc or had just begun on faculty there and was this amazing rising star in the department, and has gone on to become the, as you see here, Pritzker Professor of Radiology, and she now heads up that laboratory at U of C. So it's really a pleasure for me to be able to give this talk, and I know I'm not going to do it justice, so I'll do what I can. This is some recognition of the various grants and conflicts of interest related to this proposal, and kind of the broad themes of the work. First off, that the work that's being done in AI and machine learning is the same as and an extension of the work that's been done and continues in computer-aided detection and computer-aided diagnosis, work that's been conducted for, in fact, the last 25, 30 years. It's not just something that has arisen in the last 5, although deep learning has accelerated things quite a bit. And image-based tumor characteristics, the signatures that contribute to the design of patient-specific cancer diagnostics and treatments, are a key aspect of this. This is the precision medicine, that human-engineered features and deep convolutional neural networks can help us by serving as virtual biopsies of these tumors and provide information about lesions, and that discovery and association studies between image-based features and signatures and the histologic and genomic data can help us lead precision medicine and take that information forward. So this is kind of a framework for how AI and machine learning fit in with cancer imaging, and I think you'll see in this a number of themes that we have. First off, the question, what is the person's risk of future cancer, and that's related to risk assessment. Screening, is there a potential cancer in an asymptomatic person? What's the likelihood that a suspect lesion is in fact cancer? How aggressive is that cancer, and is the cancer responding to therapy? And we'll touch on each of these areas with the exception of risk assessment. So first off, screening, looking at computer-aided detection and providing localization. And this is something that has been in use for the last 2 decades. And in fact, you have your digital medical image displayed on a monitor and interpreted by a breast radiologist. This is in fact a system back in 1994. I had left U of C in 1991 personally, but if you look at the date that's circled there on the photograph, this is in 1994 of a system to detect mass lesions and clustered mammograms, clustered microcalcifications, pardon me, in mammograms. And in fact, it's an early example of something called shift invariant artificial neural nets, or what were in fact convolutional neural networks, that you could take an input layer and it would discern out various hidden layers to find out to output areas that had specific features that you wanted to detect. So a study in 2001 that done prospectively showed that computer-aided detection systems could increase the detection of early-stage malignancies. And in the US in particular, the number of facilities that use computer-aided detection exceeded 90% in 2008, 92% in 2016, and that's remained pretty constant. So what is the likelihood that a suspect lesion is in fact a cancer? And this is the role of CADX, this computer-aided detection. The idea being to apply characterization and classification of lesions and to basically bring to bear diagnostic biomarkers, image biomarkers that one can use. So here, the idea is to use the output to help characterize the descriptors of a lesion and potentially indicate the probability of a lesion's malignancy. And kind of stressing here as well, the final decision on patient management should be that made by a radiologist. And these systems work best when they work as a co-pilot, not as something where one is depending on the system for interpretation and then providing oversight. And that makes a big difference, actually, in the way these things work. So here, showing some decidedly benign and malignant lesions, and then, trying to identify maybe one in the middle and trying to think of how that might work. So again, the idea of having multimodal images being placed into one of these systems, and then being able to provide a diagnostic cockpit, in a way, for the radiologist to take the original images and those that are processed by these information systems in order to provide an interpretation about the likelihood of cancer and the direction of patient care management. So there are sort of two pathways that one can approach to this. One is through human-engineered radiomics, in other words, identifying the features that you want to find in the radiograph, and then creating the tools that would segment out those features, extract them from the images, and then you can run a variety of other, that you need not run a deep learning classifier. You could use something like SVMs, support vector machines, or various other tools. So here you see an example of a 3D breast image from MR, where you can see there's a lesion in the left breast there that allows you to basically identify things and potentially use the imaging technologies to gain information and identify the features of that image to use that for effectively a virtual biopsy. So the idea being with computerized, you can segment out that lesion. Find it there. Here's a tool that they've created. It's automatic, it's non-invasive, it covers the complete tumor, and it allows it to be repeatable information. So here, taking this information from these MR images, they've formed a pipeline to extract these features. They've taken the radiologist indicates the tumor center. The computer then can segment out the image, extract various phenotypic features about it, the size, the shape, the morphology, whether it enhances with contrast and what the characteristics of that contrast enhancement are, and use all of that information as part of the feature vector that describes the lesion that allows one to characterize it. So here, for example, the computer can extract objective phenotypes from breast MRI. It's not just a question of whether we as humans say that something is round or oval or smooth. You can actually put some numerical values behind that and do so objectively. Here, looking at sphericity, for example, or the irregularity of the lesions. Converting those basically, again, into a feature vector, a series of numbers that describe the characteristics of the lesion that's been identified. And as well, looking at enhancement, you can look at the heterogeneity of enhancement, you can look at the kinetics of that uptake, the washout of contrast agent. It's not just the simple question of does it enhance or not, but you can actually, again, apply very careful and very detailed information to learn more and understand the deeper properties of these lesions. So important to remember that cancer is heterogeneous. Even individual tumors display quite a large amount of heterogeneity, and what one is able to do is to take the regions of interest within these lesions, and here what she's showing is taking regions that show the most enhancing voxels and show that how those can have a different distribution throughout the lesion, that it's not just a single homogeneous lesion, that in fact, if you take these different features, the characteristics are shown with a substantial heterogeneity throughout the lesions. So the idea, again, to summarize, that you have you identify the center of the lesion, you use automated segmentation, and you identify descriptors, but these are, again, are ones that are done as human-engineered features, the ones that we select, that we think are going to be most important. And then you can merge those with a classifier, linear discriminant analysis, SVM, or some other, to yield a signature that indicates a likelihood of, that gives you an estimate of the malignancy of that lesion. So the alternative approach to doing this human-engineered is to do it as deep learning. In other words, to just give the images to the deep learning system and have it decide what the features are that are important to making the diagnosis. So again, to build one of these systems, to learn from scratch, takes millions of images. I think a lot of people are familiar with the ImageNet resource. Those who might have heard Fei-Fei Li's talk at RSNA last year learned about that. But a very effective approach is to what's called transfer learning. And there you can take the settings that come from a convolutional neural net that's been trained in one setting and apply it to a new classification task. So you can fine-tune only certain layers of the model from a pre-trained model into a new task, or use the convolutional neural net as a feature extractor by looking at what features it is identifying and finding important in the set of images that you're giving it in your new domain, and then supplying those to a separate classifying scheme to make a determination. So here, just showing an example of a convolutional neural net and how transfer learning might be worked to taking AlexNet or another model, the convolutional blocks and fully connected layers, and then this was trained from ImageNet, which has 1,000 different classes of images from natural scenes, and at the end it yields a probability that you're looking at something that's a cat or a dog or a giraffe or any other, or a car, or whatever it might be. But the idea that you can then extract portions of that trained model to use those for transfer learning. So here, actually taking information out and taking some of the layers from the network that had been trained with ImageNet, doing a dimension reduction on that, and using that on breast cancer data to come up with a probability that a lesion is breast cancer. Again, so here, the layers that it's picking out are these max pool layers within it that are not the final outcome, but in fact are intermediate features that the network has identified along the way. So just using it as a tool to identify the features within that might be important for classification. So one of the things when you combine this is to combine conventional CAD and radiomics with deep learning. And these data points that you see here, the ones in red are cancer, the ones in green are non-cancer, and it's plotting the likelihood of cancer as determined from conventional computer-aided detection as opposed to deep learning. And ideally, you'd like to see these kind of overlap and be the same, but in fact, you can see that the two systems actually work nicely together. And so you have areas like this where one of them says that this is likely to be cancerous, but it's been missed by conventional detection. And similarly, you have lesions up here that the conventional CAD says might be positive and were missed by the other system. So the advantage of this is that you can combine the two. And the idea here that Marilyn put in is that having those of you who may be kind of new to this terminology, one of the most powerful techniques, it turns out, in AI, a very interesting technique, is something called an ensemble classifier. So if you have two classifiers that are independent of each other and kind of think independently, use different methods to come to a result, combining the two will actually yield even greater performance than either one alone. This is kind of the notion of double reading in mammography, the idea that two readers might have different capabilities, but the combination of the two together improves it. Same thing with human and AI, that typically the combination of human reader and AI reader improves the performance of a diagnostic system. So here, taking the combination of conventional CAD and deep learning CAD and using a fusion classifier. And what they were able to show was in all of these for mammography, for ultrasound, and for dynamic contrast enhanced MR, that the combination of conventional CAD along with the deep learning, the CNN approach, produced a great higher value for the area under the ROC curve for in all of these areas, from using it as an ensemble, using it as a way to combine these techniques. So here's a slide that shows the effect of 3 of the MRI input protocols on performance for a malignant lesion. Part of it is looking at how the image sequences we choose actually fit into how we're able to do things, both garnering 2-dimensional information as well as the 2-dimensional plus temporal information, as well as volume information about those lesions. And what one is able to show is that as one adds these additional pieces of information into it, you can improve the performance of your classifiers. So it's incumbent on us in terms of developing these systems to incorporate as much information as we can and to provide access to that information for classification purposes. And here's, this is a paper that describes a workstation for high throughput phenotyping of breast lesions. It does a number of things. It actually takes, you can take a lesion and then based on your current mouse location, it will give you information about the average kinetic curve and the contrast enhancement kinetic curve for that point in the image, as well as giving you computer extracted information that describes the morphology, the volumetrics, the texture kinetics, and an estimation of the probability of malignancy of that lesion. So here, you can see that for various areas within lesion, it's giving this probability of malignancy for at a specific point in the image. So in other words, over that identified lesion here, and being able to classify that and put that give you graphical feedback about the probability of malignancy for that lesion. And this is a system that they're in the process of translating and commercializing. And Mary Ellen mentioned to me that this is the first system that's actually cleared FDA for a machine learning system in cancer diagnosis that uses some of this information that actually looks at 3D information and the the contrast kinetics in terms of this information. So the other aspect of this is doing an assessment of prognosis, looking at how aggressive the lesion is and coming up with image-based prognostic markers and determining whether or not a lesion is responding to treatment. So here you have the medical imaging information and you're feeding it both to the radiologist and to the computer vision system and coming up with classifications ideally, and you have as well histopathology and molecular classification information and data from genomics, and all of this can be used to identify associations and classifications relevant to important clinical and biological questions about these tumors, and to enable us to develop predictive models to really create personalized or precision medicine tools and approaches to address these lesions. So, the question is, in terms of gene factors, which are correlated, which are synergistic, and using the computer vision tools, using radiomics and quantitative measurements to really drive medical imaging information. And really, the hope is that by capturing this information in a more quantitative form, that we can actually improve our understanding and drive these correlations in order to better elucidate the biological behavior of these cancers. So, question, how do we harness imaging big data? And there are really 2 stages to it. The first is discovery, finding relationships, scouting the data, looking for potential relationships between imaging data and all the other information that's out there, clinical information, molecular data, genomics, and outcomes. The second part of that is application stage, and that's developing predictive models for risk assessment, for screening, for detection, diagnosis, prognosis, therapeutic response, risk of recurrence. But it's kind of a two-stage approach to accomplishing all of these. So here is a model for discovery and modeling of personalized care, starting with screening, diagnostic imaging, treatment planning and response, and risk of recurrence, using the information from diagnostic imaging to link to biopsy results and genetic testing results, to be able to look at imaging, doing those sort of maps of imaging phenotypes and gene expression data to do imaging genomics discovery, and then taking all of that information to create predictive models of cancer behavior. And this is this notion of virtual digital biopsies, being able to actually capture information about the lesion without having to do anything other than imaging it, without having to actually take a biopsy. And you can use the idea here too that you can use virtual biopsy when an actual biopsy isn't practical in a patient. So here's an extension of that showing characterization of cancer subtypes, tumor grades, looking at a classification of markers for breast cancer, IDC grades 1, 2, and 3, and benign, based on, as you can see, various imaging phenotype features, irregularity, circularity, various others, and looking at how those map out to these different tumor grades. I think she has, yeah, here, showing a plot that shows how this is able to distinguish based on the information gain, the entropy, based on the characterization of the different types from the ability to detect those from the actual information contained in the imaging study. And then this was taking a subset of one of the Akron studies to do images where they looked at women who were imaged both at baseline, pretreatment baseline, and those imaged after completion of first cycle of chemotherapy, and looked at recurrence-free survival early on based on characteristics of that. And what they were able to show was, as you can see here, taking lesion identification, which was done manually, but then using the computer to automatically segment out those locations to look at the kinetic curve of contrast enhancement and identify the most enhancing tumor volume, and then be able to plot that and connect that with survival rates. And actually plotting Kaplan-Meier recurrence-free survival estimates based on this most enhancing tumor volume in early treatment time. And as you can see, they were actually, it has correlations with hormone receptive positive and HER2 negative disease, HER2 positive, triple negative, and so forth. In other words, correlating the behavior of these tumors with known tumor markers and being able to, this is kind of an example showing how this information can be used as virtual biopsy. And also looking at this as a predictor of recurrence, where you can see a case here that they've identified as a luminal A type, and then with this multi-gene assay of risk recurrence, and then various tumor markers that they were able to characterize and segment out these populations based on imaging information alone. So again, kind of taking some of this information from TCGA and TCIA, the various information, integrating it in radiogenomics and using this to identify genetic pathways, to do look at mutated genes and microRNAs, and to do cluster analysis to look at tumor subgroups. Basically, again, really working to elicit the tumor biology in these lesions. And I guess I would just make a plea in here too. This is not only an opportunity for computer scientists who do the deep learning and for those of us in radiology who look at the clinical aspects, but it's an opportunity to connect with our colleagues in pathology and oncology to work closely with them to elucidate these factors. And again, you can do exploratory cluster analyses to look at these tumor phenotypes in this case, found significant associations between radiomic features and clinical outcomes and t-tests and use that to cluster. I'm just going to make sure I cover things towards the end here, some features that are identified, and then just, again, some of the future potential and plans for AI. The important thing is the specific task, the clinical question, the images, the workflow enhancement, looking at the data, making sure you have images and satisfactory ground truth to work with, and be very cautious of garbage in, garbage out. Make sure the data that you have are robust and that you are well validated, and that you can use this to answer some biomedical question, use it as an aid to a radiologist. And you have to understand how you're using this AI. Is it meant to be an aid for radiology? Is it meant to be used as the primary reader? Or is this meant to be more of a discovery tool? So just in conclusion, again, look at the lessons learned from CAD systems. In fact, radiomics and machine learning have been around for quite a while. In fact, since the 1990s, we need to collect and curate data sets to provide truth for training and testing. We need to be aware of pitfalls such as subtle disease presentation, and this example of the system that detected not pneumothorax, but it actually found chest tubes was how it detected pneumothorax. And we have to conduct AI about medical imaging by knowing about medical imaging, and interdisciplinary research is critical. And acknowledge that AI will augment interpretation, handle routine and tedious tasks, integrate diagnostics, improve performance, reduce interpretation times, and we have to make sure we integrate machine learning into the clinical workflow, have in the US FDA clearance so it can be used in clinical practice. Within the clinical workflow, we have to collect data efficiently to support future research. And a key area we haven't really talked about that much is this area of explainable AI or interpretable AI, to be able to understand what it is these models are generating for us. So with that, on behalf of Mary Ellen, thank you for your attention, and appreciate. This is her research group from at University of Chicago. In the summertime, she mentioned, when it's nice in Chicago. Thank you.